John here. Let's talk about object conversion or conversion operators, okay? So we saw this complex class before. In this version, what I've done here is I've just inlined all of the operators. In the last lecture, we talked about overloaded operators. I introduced a lot of these. They were all done as friends. In this case, we're doing them in line. I can inline any operator where the left-hand side, right? And what by that, just a quick review here. If I want to add two things together and I want to add a complex object plus a complex object, I'm talking about the data type on the left of the operator here. So this is the left-hand side and the right-hand side of the operator, okay? In this case, the operator is a plus. If the thing on the left is the type of the class that I'm defining right here, right? Complex, okay? And I want to put an operator in here that says I want to have complex plus another complex on the right side. I can just put them in line like this, okay? That's my whole point. So when you do that, the thing on the left is this variable, right? So I can just grab real from this and the real from the right-hand side, add those two together, and the same thing with the imaginary side as well. Okay, and the same thing happens if I want to add an integer to a complex, all right? Returning, again, a complex. So what do we do if I'm adding an integer? Really, I just add the integer to the thing on the left, which is this, and the imaginary part stays the same. And I return that, right? Oh, we went over this before. Now, I did fix something. In the last video, I was scratching my head. I don't use complex numbers very often, and I did look this up. The unary negative in the last video was incorrect, okay? This one is correct. I looked it up. When you negate an imaginary number, you have to negate both the real and the imaginary components of that number, okay? I wanted you to see this in particular right now. That's why I'm dwelling on this. The unary negative has no right-hand side, okay? You're negating this, even though when you use it like this, right? You would negate a complex object or something like that. It is on the left, but you know what I mean. It has only one operand, which is this in this case, okay? So this is what it ends up looking like. So the unary negative has no other operands, okay? So that's what this thing looks like, all right? And yes, I fixed it. So don't bother if you, unless you already have, don't bother throwing too many comments in there about that being wrong. Anyway, here's what an assignment operator looks like if you inline it and so on, right? This is not an assignment operator. This is a relational operator, right? The double equals is the relational operator. This is the assignment operator run right down here. And again, this can only be done inlined like this, or at least as a member function. It cannot be done as a friend, I should say, because the language necessitates that, all right? Now, what have I done here? I've kept the insertion operator, and it cannot be done as a member function. It has to be done as a friend, because the thing on the left-hand side is not of the type of the object within which I'm using this and defining it, right? And I create this as a friend because when this runs, the item on the right-hand side needs to have the ability to reach in and grab the private parts of the complex object in order to do what it wants to do. In this particular case, it could use the accessors if I wanted to. But it in any realistic kind of object that has a lot going on, you might need to reach in and grab the access to the private parts of the instance. So it's very common to do this as a friend like this, okay? So what's the whole point of this thing? Just a quick review of where we're at and how the complex numbers work, and a demonstration of the fact that I fixed my unary operator there. So let's go ahead and run this, and voila, 1.2 plus 3.4i, and negate it, and you end up with negative 1.2 minus 3.4i, okay? So let's look at now the differences between this and this one. numbers 9 and 10. So here's, what if I want to do something like this? All right, so the differences between version 9 and version 10, I'm throwing away these comments, and I'm going to create a double, and I'm going to try to add a complex number to just a double, all right, and then print it out. So let's look at it. The actual file, if you can't visualize all that, what you saw is me removing the negation and the printing. That's stuff from version 9. And here's this double, and I'm going to try and add a complex, which is what C1 is, to a double. And we'll see what happens here. So let's try and compile it. The compiler is going to gripe. Now look very closely at what it says here. I cannot find an operator plus equals where the operands are double and complex. And this is written so that the double is the thing on the left. You can clearly see that's the double over there of this operator. And the CPLX object is the thing on the right. So it wants to find an operator plus equals that takes a double and a complex in order to do its job. Well, let's take a look at the differences then between 0010 and 0011. And we'll see that in version 11, what we're going to try and do is we're going to provide an operator with a double on the left and a complex on the right. Now, because the thing on the left is not a complex, I can't do this with a member function. I can only do it with a friend. And I can implement the friend like this. Now, when you convert what we're really doing here is you have to convert the complex number into a regular number, right? A non-complex number. And the way you do that is you find the magnitude of a complex number, okay? And then you add that to the double. I suppose you could argue a couple of different things here. Let's just assume that what we want to do in the semantics of our object, if we ever want to add a complex to a non-complex, what we want to do by definition is in our class is what we really want to do is add the magnitude of a complex number to the non-complex number. And the way you do this is you add what is essentially a hypotenuse of a right triangle. If you Google around and find out what a complex number really is, it's a value on a two-dimensional plane. And there is a thing called the magnitude, which represents the hypotenuse of what would be the right triangle given by the real part on the x-axis and the imaginary part on the y-axis. All right, so let's go ahead and compile this and see what happens. Oops, if I type it in correctly. It compiles. Gosh knows what it's going to do, right? Especially if I don't type it in right. I'm really good at mistyping. 127.062. Well, what is that all about? Well, let's have a look-see here. So we got 127.062. Well, the magnitude of this complex number, if you think about it, is around 3. Okay? In fact, we could find out quite easily what it is by simply printing it out. Let's set the double to 0. Right? If we add it to 0, we'll find out exactly what the magnitude is. Oops. Again, if I can type, I'm really not banging on all cylinders here. Make 0011, 0011, and we got about 3.6, okay? That seems reasonable. So that's all exciting and dandy, but there's another way that we can use to fix this problem, which is this conversion operator. All right, so let's look at the differences. I guess let's first do that. 0011 with 0012. So the differences between 11 and 12. 11 is the one we just ran, right, with the code up here that where's my last if? In number 11 we added this right here, which does the the hypotenuse calculations. Okay, no big deal. You essentially define the operator plus equals and all this stuff and all the data types pretty much the same way you did the insertion operator, right? When you have an O stream and you return the O stream reference and so on. Okay, now in the conversion operator, the way we write these is we say this is the output time. This is a kind of a screwy way to define functions in C and C++. This is the only thing that I'm aware of that kind of works this way. So bear with the weird way of expressing these. What happens is this is a double operator, right? This is just like operator minus, operator plus. This is operator double. And since this is all text, you have to put a space in there. This is just how the language is specified for this sort of a thing. So what this really means is this is a function that will provide the ability to convert whatever the object is that this member is defined in into this double. Okay, I want to make a double out of my CPLX. Well, how do I do that? Well, that is, in this case, I'm going to just use the magnitude, all right? Now, I'm going to print out a message when I do this so that we can know this function got called. I'm also going to print out a message over here, and you're going to see when we look at 0012 that comes from the plus equal operator. In fact, I'm just printing out the function signature that's executing, just like I did here, inside this overloaded operator. So we know if it used that code. All right, now in the main, what have I done? I've changed the 0 to this. Yeah, this I just, because I made it 0 in version 11, version 12 is really no change for what 11 started at. So let's go 0012.cc. Go down here. So what did I do, right? From the diff, all I did is I added this thing, okay, and some comments. And this is the comment that really matters right now. So the compiler is going to come around here and say, hey, if I ever need to make a double out of a complex, I can use this, all right? And I can just go and grab it. Whatever this code says, I'll use that, and I'll make a double out of it. Well, what does this thing do down here, right? Well, let's think about what the code really is doing. I have a double, and the double has a value. And I say double plus equals complex. There's kind of two ways to solve this problem. Ultimately, I'm storing the result in a double. So I could either go and grab this operator that says I got a double on the left-hand side, a complex on the right-hand side, and I'm trying to execute a plus equals operator. Well, that's a real good match right here, okay? So the compiler could go in there and use this code to perform the addition, and it can get a double result out of it, okay? All this has to match. So the compiler knows the result has to be a double. It knows that the double is on the left-hand side of this plus equals operator, and it knows that a complex type is on the right-hand side of that operator. This is a perfect match, okay? The other way the compiler could do this is it could say, I got a double, and I'm going to plus equals something else over here. And it could say, well, I know the result is going to be a double, so I really need to convert whatever's over here into a double. So I can add it to D. All right, there's a completely other way to do this, and we've given it the ability to do that now. We've said anytime you got a complex, you can convert the complex into a double by using this code. So what we've done is we've created a conflict for the compiler to resolve. All right, that's exactly why we printed these statements in here. So which one is it going to use? What we'll see is when it has more than one option, it'll use the most specific operator, the most specific function that it can to do this job. And because we have a perfect match here and a good match over here, this one will be used. It matches better, all right? It has to do with the order in which it tries to figure out, I want an exact match, then I'll try and make it work out of something else, and it lowers the priority of just the conversion operator, okay? So let's go ahead and compile 0012 and run on 0012. And we can see it did, in fact, use this exact match function, even though I provided the other one, right? Because this one simply matches better. And we should hopefully get the same results each time. Number 11 had 360. Let's go ahead and put 11 back to the way it was so we know that everything matches okay. All right, so we're just playing around with that. And yes, we did. 127.062 for each of the two cases. And that makes perfect sense because they both called this, right? In version 11, it had no option. It only had this function here. In version 12, we give the compiler a choice. You can either use the same thing it did in 11 and get the same results. Thank you. Or you could convert the complex number to a double first and then add it to the D. Okay, so let's look at the diff now between 0012.cc and 0013.cc. And what we see, the only difference here is I added if0 and endif, another if0 and endif to the code. All right, let's look at what I did there. That just commented out two sections of code, right? And it'll turn blue in this particular editor. I commented out the declaration that provides the friend attribute of this operator, okay? And I can completely commented it out down here. So the compiler does not have this at its disposal. The rest of the code is exactly the same. The diff shows no other differences, right? So let's see what happens if we make this. And you should be able to guess by now. Well, if it can't do one way, it'll do it the other way. We get the exact same result because mathematically, in this particular case, it literally will give you the same answer anyway. Ultimately, it's the same code due to the nature of this particular object, all right? And that is the fact that inside the plus equals, it says, square root of the sum of the squares and so on. Doing Pythagoras here, and I do Pythagoras up here exactly the same way. The one down here includes the addition to the left-hand side. The one up here does not, and the addition is performed down here in the case where the double operator is used. So it's literally the same instructions being done, but for different reasons, right? Because we're using a different style of overloaded operators, all right? Now let's take this a little bit further. Let's differentiate between 13 and 14 and see what we're going on with that. Okay, what happens here? So in version 14, I've simply added these three lines of code to the main. Let's get a bird's eye view here. I've added these three lines down here, okay? Everything else is the same. But this time I've created an integer, and I say I want to add C1 to an integer, and then print out that integer. Well, what's it going to do now? Well, even if this was here, right? This is the one that says I can add a complex to a double. Well, I can't really do that because I'm not adding it to a double. I'm adding it to an int. And I provided this overloaded operator that does a conversion from complex into a double. And the compiler needs to convert one into an integer to do this, right? Obviously, it converted it to a double to add it to the D. Now it's going to try and need when it goes to an integer. So what's it going to do now? Oddly enough, there's no errors, right? So what is it going to do? Well, it actually, notice it calls double twice, all right? Now, this is because... and this is one of the benefits of using this technique, all right? Let's go back and look at 14 again. It wants an integer. It can't add a double to an int. The computer really can't do that. But it can convert a double to an int. The compiler already knows how to do that. So when it's trying to figure out how to do this with what we've given it to use, it says, well, I want an int in order to add it to this int. And it'll look around to see, do I have an int reference operator plus equals int reference left and context complex right hand side. It wants an exact match. And it'll look around and says, no, the guy didn't give me that. I say, well, I don't have that, but I'll try and find a conversion operator like this that says operator int. And I'll try and use that. Well, it looks around. I didn't provide one, so it can't use it. It says, well, I can make an integer out of a double. I can make an integer out of a float. I can make an integer out of a short or a long. all kinds of things the compiler knows how to do using its standard coercions. So what happened here is it eventually said, I'll try this, I'll try that, I'll try something else. And it found, oh, wait, I can use a double. I can convert the complex to a double. Then I can convert the double to an int, and then I can add it to the I. All right. Now, that's a lot of code if these are, really nasty, complicated objects. So you got to be careful when you're doing this sort of thing. This is starting to increase the cost of running this program, okay? So don't just take this all willy-nilly, all right? But it's nice to know it's there if you need it, okay? Let's look at this next one. 14 versus 15. So the only difference between 14 and 15 now. Remember, 14, I simply added the integer one. I want to try to add a complex to an int. In 15, I removed the if zeros. So let's take a closer look at 15. All right, nothing changed down here in main. The only difference here is the plus equals is no longer commented out. Okay, and the declaration of it being a friend up here is also no longer commented out. So let's compile this and run this one. See what's happening now. So this really demonstrates the pecking order of what's going on. And what I said earlier, it'll try to use the most specific thing it can and then progressively fall back into more general types of data that it knows how to do conversions on. So clearly, when I'm trying to do a double plus equals complex, and I have a function there that does exactly that, it's going to use it. But if I have an int plus equals complex, this really doesn't cut it doesn't cut it. I have to convert it to a double first, then I got to convert it to an integer, all right? So this is a little bit of an insight into how these conversion operators work, all right? So you can get a lot of mileage out of just saying, here, compiler, I'll convert it to something you know how to deal with and let the compiler run with it from there. As that bought us integers, shorts, signed, unsigned integers, 32 bits, 64 bits, all these different kind of data types with one simple conversion operator, all right? And if it's acceptable for your math, in this particular case it is. In fact, this one thing gives me just about anything I need. I don't have to define all these other types with all these friends. What if I want an and, a double, a short? You don't have to do all that, okay? If it matters to the precision of your results, or your application needs to do things in different ways, if the types change, then fine, add all you need. However, this allows you to boil it down to a minimum set and make things a little bit more manageable. So, thanks for watching. See you next time.